Well, very last thing you can calculate. You should ask yourself, what can I calculate about this system, model system, because statistical mechanics is model dependent. Depends on what model you are using or solving. So this is classical ideal gas, non-interacting particles, indistinguishable. You can ask yourself, what happens if they are distinguishable? Huh? Keep asking yourself questions so that you are ready for the exam. For example, if I asked you to calculate the chemical potential, could you do that? Let's calculate chemical potential as our last quantity. Can you read the things that I'm writing? Okay. Qn Vt we know, V to the n factorial, lambda t to the 3n. Q1 to the power n divided by n factorial. Partition function we know, exponential zv over lambda t cube, explicit v and t dependence. PV we know, kBt ln partition function, ground canonical partition function, that is kBt zv divided by lambda t cube. Okay, so we can write pressure as kBt z over lambda t cube, or we can invert to get z. Chemical potential is in z, you know. So z is P over kBt lambda t cube. Since z is e to the beta mu, we can get mu, the chemical potential. So mu is kBt ln, take logarithm of both sides, exponential gives beta mu. There you can get beta mu is mu giving kBt times logarithm of the other side, which is P over kBt h squared 2 pi m kBt to the power 3r. This is lambda t cube, isn't it? So we know for classical ideal gas PV is n kBt. So P over kBt is n over v. So mu comes out to be kBt ln n over v lambda t cube. Very simple calculation. You should also ask yourself questions about other quantities I didn't calculate. Explicitly, you can do everything yourself. Do you have any questions about classical ideal gas? Is everything clear? I used my grand canonical ensemble ideas to get the earlier results. as explicit functions of volume, temperature, pressure, etc. Whatever is the way you want to write them. Any questions? Okay, let's go to example number 2. Now this time I'm going to take localized particles for my example. The model is a system of independent and localized particles. So it is like solving problems, right? Localized. Particles. What is the meaning of localized particles? What does it tell you about? Distinguishable. Localized means they are sitting at certain points. So by their positions, we know where they are, which particle is at what position. So they are completely distinguishable. So the meaning of this is that the particles are distinguishable. That's why I wanted to do this, because in the first example, the particles were indistinguishable. Let me do this problem in general, then specify the system later. Okay? We can solve the problem in very general terms as follows. First, if they are distinguishable, I can write the canonical n-particle partition function in terms of single particle partition function, simply raised to the power n. You don't divide by n factorial. Indistinguishable particles has that. So if I do this, then I can write everything in terms of single particle partition function. Let me call that, instead of writing this as Q1 Vt, let's be lazy again, write this as a function phi of t. Okay? Now, the reason is going to be simple, because I'm going to write all my results in terms of this function, one particle partition function. Then all I have to do for specific examples, calculate the single particle partition function. And that's it. I have all the other expressions coming out. Now, in terms of this, let's calculate the ground canonical partition function, ZVT. It is the usual definition. No n factorial. They are distinguishable. So it is a simple power series, and the result is 1 over 1 minus x, which is z times phi of t. So if you know the single particle partition function, canonical, you have the ground canonical partition function. Okay? So, Again, for convergence, Z phi t this time must be smaller than 1. The thermodynamics is quite easy to get after calculating this grand canonical partition function. Pressure, same program as you see. Or kBT over V. Q was logarithm of this grand canonical partition function. So it is ln 1 minus z phi. Why? Because ln 1 is 0. Isn't it? ln 1 minus ln 1 minus z phi t. So we have to have the negative sign, of course, ln 1 minus this ln. So the Q potential ln of grand canonical partition function is minus ln 1 minus z phi t. Everything comes out nicely, clearly. Mean number of particles, z, del q, del z, keeping temperature constant. Taking derivative of this is quite easy. I'm not going to do these explicitly, but let me do it once at least. 1 over the function times the derivative of the function minus phi of t. So n comes out to be z phi of t divided by 1 minus z phi of t. If I know the single particle canonical partition function, I know the n. I know the pressure. Okay? Should I calculate pressure? It's nonsense because there nothing depends on volume. You won't get anything. But I can calculate energy minus del beta of ln of q keeping z constant. So that gives us kb t squared. Please do these calculations yourself, okay? Check my notes. I may have some mistakes in my writing. Don't trust me. kb t squared z times d phi dt divided by 1 minus z phi. That's the expression. So if you know phi, single particle canonical partition function, you know energy, pressure, number of particles, everything. Similarly, you can get the Helmholtz free energy everything is coming clearly, explicit function of phi, entropy, we don't calculate pressure as I told you. We can even simplify these expressions a little bit further by using the following fact. May simplify well, we know the number of particles as z phi divided by 1 minus z phi. This gives you a z phi, which is equal to n minus nz phi. Or take into z phi parentheses 1 plus n equals n. N is a large number, isn't it? So z phi is n divided by n plus 1. And you know n is a very large number of particles in your system, localized particles. Here comes the approximation. Well, you can take into n parentheses the denominator, it becomes 1 plus 1 over n. N will cancel, 1 over 1 plus 1 over n is 1 minus 1 over n, isn't it? So you can approximate this as 1 minus 1 over n. That's the large N approximation. Using that, you can simplify our expressions further. As follows. For example, the energy can be written as KB, well, 1 minus we have this factor, isn't it, in our expressions that can be written as 1 over n from that relation. Huh? So using this, U becomes KB T squared Z times derivative of Z divided by 1 minus Z phi. And that becomes n kbt squared times z times derivative of phi. That's the simplified expression for energy per particle, then becomes kb t squared phi prime. You cannot go any simpler than that, isn't it? Energy in terms of derivative of single particle canonical partition function. Well, you can even do it a bit more. Because you know, 1 minus z phi was 1 over n, and z phi is n minus 1. But n is a very large number. You can safely omit 1 here, isn't it? So that's n. 10 to the 23 minus 1, 10 to 23. So z is 1 over phi. Of course, you can do that for a solid, for example, because n localized particles can approximate the solid, isn't it? N localized ions are sitting at lattice points. So you can use this model to model a solid. In metals, electrons are completely randomized. They are all over the solid. What are localized are ions. For insulators, you have localized ions sitting at certain positions, so perfect for this model. Okay? Or the localized particles can be considered as localized harmonic oscillators. Ions are vibrating at their lattice points. So harmonic oscillator problem can also be solved by this model. So this gives us energy per particle as kBT squared phi prime over phi, completely in terms of single particle canonical partition function. If you know that, you know energy. Again, this similar calculation simplifies further thermodynamic quantities like Helmholtz free energy per particle comes out to be minus kBT ln phi plus terms of order ln n divided by n, and that is negligible. You can omit those terms because n is a very large number, and entropy in units of nkb can be written as ln of phi plus t times phi prime over phi plus terms of order ln n over n again. So you can omit that too. So knowing phi t gives us everything. So the question is, what is this phi for localized particles? One particle canonical partition function for localized particles. If we know this, we know the thermodynamics. That is our problem now. Should we calculate it for some models? Would you like the calculation of phi t for some models? Like localized harmonic oscillators, etc. Should we do it? Or can you do it? Let's do it. Let me calculate phi t so that I can use these expressions for some model systems. Example, let's take one-dimensional quantum or classical. Let's take the quantum harmonic oscillators as our model. Quantum so for this application, we have to know the energy levels. Very easy to generalize to 3 dimensions. N plus 3 alphas times h bar omega, isn't it? So, one particle partition function, which is our phi t, which is nothing but a sum exponentials beta en That's it. We have to do this sum. Can we do this sum? Very easy. That term is constant. We can take it out of the sum. E to the minus beta h bar omega over 2. So it is e to the minus beta h bar omega over 2. A sum e to the minus beta h bar omega n, where it is like exponential minus h bar beta h bar omega to the power n, power series, 1 over 1 minus the exponential. So it is well, we have twice the same quantity, isn't it? We can take that denominator to the parentheses e to the minus beta h bar omega 2, then I have a positive e to the beta h bar omega 2 and negative e to the minus h bar omega 2. So that is 1 over e to the beta h bar omega over 2 minus e to the minus beta h bar omega 2. We know that it is 1 over twice the sinus hyperbolic beta h bar omega over 2. Very simple calculation. It is only the function of temperature. Beta is 1 over kBt. So this is phi of t. Use this in all the calculations, all the expressions I have given to you to get the pressure, no pressure, of course 0, and energy, number of particles, etc. Is that okay? Let's do classical one-dimensional harmonic oscillators. See, there are variations. The same model can be done in a couple of different ways. They constitute different models then. So you can do the calculation for those cases too. Classical. Each one of these different examples or problems. Here is a one-dimensional classical harmonic oscillator. In this case, Hamiltonian is having a kinetic energy part plus a potential energy part. What is the potential energy in this case? 1/2 k q squared, isn't it? K is m omega squared, so it is 1/2 m omega squared q squared. Classical PQ. Remember, momentum position. One particle partition function is, well, of course, the sum turns into an integral in the classical case, and one dimension, you cannot separate the volume term because there's q in the Hamiltonian, is like 1/h instead of L/h e to the minus beta p squared over 2m plus 1/2 m omega squared q squared, the Hamiltonian. Canonical, you remember, e to the minus beta e dp dq, isn't it? Since we are dealing with a one-dimensional case, this is the infinitesimal volume in phase space divided by the h, which was corresponding to fundamental volume, isn't it? That's the density of states, concept of density of states. Do you know the concept of density of states? So I have to go through that too. I have to spend my time for undergraduate training. Okay. Well, we know the integral, Gaussian integral, e to the minus alpha x squared dx. We have two integrals multiplied together, pi over alpha square root. Using this, we can write the integrals over p and q explicitly, very easy. So in this case, phi of t is 1/h square root 2 pi m over beta to the power of 1/2 times 2 pi beta m omega squared 1/2. I have done this calculation before when I did the same problem in microcanonical case or canonical case. I'm just repeating it. 1/h 2 pi beta omega. So that is our beta is kbt, 1/kbt, it goes up, kbt over h bar omega. So 2 pi h bar, h over 2 pi is h bar, isn't it? Very nice. kBT is thermal energy. This is the energy difference between levels, isn't it? H bar omega. So that's our result. 5 prime is easy in this case, very easy, with respect to temperature. Gives you this. And you can calculate energy, for example, as kBT, or energy is N kBT. Did we get the same result before? Of course. I have done an explicit calculation. You can repeat this for other thermodynamic quantities, and you get Helmholtz free energy, entropy, etc. for this classical problem. Helmholtz free energy per particle comes out to be minus kBT ln kBT over h bar omega. Entropy in units of nkb. Check these. Ln kBT over h bar omega plus 1. These are the canonical results, canonical ensemble results. So everything comes out. Do we have any questions? How are you doing? Are you following everything? Are we going in a correct pace? Too fast? Too slow? Just right? Which one is correct? Is it just right? Should I get faster? No. But one thing that bothers me, you are not asking any questions. I'm almost begging you to ask questions. You can only learn by asking questions. And keep it a habit to ask questions about what we are doing. What happens if I consider another example? How should I solve it? Okay? You should be able to start thinking in statistical mechanical terms. Don't memorize anything. Do them. Okay, I think it's time to quit. Thank you very much.